In this lecture, we show how one can use the method of false position or the Regula Falsi method to approximate the solution between x equals 2 and x equals 4 of the equation x times sine x plus cosine x equals 0. The approximation should be within 10 to the minus fifth power of the exact solution. Let f of x be equal to x times sine x plus cosine x. F is a continuous function, and in addition, rounded off the three significant digits, f of 2 is 1.40, while f of 4 is minus 3.68, so that f of 2 and f of 4 have opposite signs. And so the intermediate value theorem guarantees that there is at least one solution between x equals 2 and x equals 4 to the equation x times sine x plus cosine x equals 0. One can also show as an exercise that the derivative f prime is less than 0 on the interval between 2 and 4, and that therefore f is strictly decreasing on the interval between 2 and 4. Hence, f of x equals 0 has only one solution on the interval between 2 and 4. Let x equals r be the unique solution to f of x equals 0 on the interval between 2 and 4. At the nth iteration, or iteration n, with the interval a sub n, b sub n, we denote the method of false positions or the Regula Falsi method's approximation for the root x equals r by c sub n. C sub n equals a sub n minus f of a sub n times the quantity b sub n minus a sub n over the quantity f of b sub n minus f of a sub n. In order to determine the endpoints a sub n plus 1 and b sub n plus 1 of the next interval in which we look for the next approximation c sub n plus 1, we consider the sign of the product of f of a sub n and f of c sub n. If f of a sub n times f of c sub n is less than or equal to 0, then the new left endpoint a sub n plus 1 is a sub n, and the new right endpoint b sub n plus 1 is c sub n. If this inequality fails, then the new left endpoint is c sub n, and the new right endpoint is b sub n. We are going to use the software Mathematica for our calculations. First, we define f of x. F of x equals x times sine x plus cosine x. The first left endpoint a sub 1 is 2. And the first right endpoint b sub 1 is 4. Because the method of false position is recursive in nature, we use a do loop. The first command in the set of commands within the do loop is the definition of c sub n. C sub n is equal to a sub n minus f of a sub n times the quantity b sub n minus a sub n. In this, we divide by the quantity f of b sub n minus f of a sub n. Having defined c sub n, we now print a sub n, b sub n, and c sub n on screen. We also print the iteration number n. After each time we calculate and then print c sub n, we determine if we have already reached the prescribed accuracy of 10 to the minus fifth power. In order to test the accuracy of c sub n, we check the sign of f of x at a distance of half the prescribed accuracy to the left of c sub n, and then again at the same distance to the right of c sub n. So we check the values of f of x at c sub n minus 0.5 times 10 to the minus fifth power, and at c sub n plus 0.5 times 10 to the minus fifth power. If f of x has opposite signs at these two values of x surrounding c sub n, then by the intermediate value theorem we know that r is somewhere on the interval between these two values of x. And since c sub n is the midpoint of this interval, c sub n will be less than 10 to the minus fifth power from r. We test the condition that the product of f of c sub n minus 0.5 times 10 to the minus fifth power and f of c sub n plus 0.5 times 10 to the minus 5th power is less than 0. We must also allow for the possibility that r ends up being equal to either endpoint. This would make the inequality false and have us throw out the actual root. Therefore, we change the inequality from a less than inequality to a less than or equal to inequality. If this inequality is true, we want the calculation to stop, and we break out of the do loop. If the inequality is false, then we do nothing to stop the calculation. We then determine the endpoints of the new search interval. This time, we test the product of f of a sub n and f of c sub n. If this product is less than or equal to 0, the new left endpoint a sub n plus 1 is a sub n, and the new right endpoint b sub n plus 1 is c sub n. Otherwise, or else, a sub n plus 1 is c sub n, and b sub n plus 1 is b sub n. To finish the do loop, we put a cap on the number of iterations. Let's have n go from 1 to 10. We evaluate this cell of lines of code. C sub 7, which is 2.79838, is the final estimate for the root r. The exact root up to 7 significant digits is 2.798386.